In question 1, we are asked to find the first 4 terms in ascending powers of x for the binomial expansion of 8 over 2 minus 5x to the power of 2. So the first thing to do is write what we are given as 8 times 2 minus 5x raised to the power of negative 2. I will factor out the 2 to get 8 times 2 to the negative 2, so we inherit the power of the original expression here, and I divide everything with 2 within the bracket, so it's going to be 1 minus 5x over 2 raised to the power of negative 2. So we are looking at 8 times a quarter, so let me write this down. It's 8 times 1 over 4. And then we apply the binomial expansion. So we need to have 1 plus or 1 minus something in order to proceed with the binomial expansion when the exponent is negative or fractional. So we're looking at 1 plus the power of negative 2 times minus 5x over 2 plus the power of negative 2. I will deduct 1 from the power to get negative 3 over 2 factorial times minus 5x over 2 raised to the power of 2 plus negative 2 times negative 3 times negative 4 over 3 factorial times the minus 5x over 2 raised to the power of 3. So we've got an infinite number of terms. I stopped up to the term in x cubed because I'm being asked to find the first 4 terms. So we've got 8 times a quarter, which is 2. And within the bracket, we're looking at 1 plus 5x plus 75x squared over 4 plus 125x cubed over 2 plus dot dot dot. I will further expand this to simplify the whole expression, which is 2 plus 10x plus 75x squared over 2 plus 125x cubed plus dot dot dot. In part B, we need to find the range of values of x for which the expansion is valid, and let me start by reminding ourselves that once we put the bracket in the form of 1 plus or minus something, then the expansion is valid. For this expression here, its absolute value being less than 1. So let's take a look at what we've got here. We've got 1 minus 5x over 2. So in our case, the expansion is valid for the modulus of 5x over 2 being less than 1, which simply means we're looking for values of x which have an absolute value less than 2 over 5. In question 2, we've got this cube which is increasing in size. We are told that the length of each edge is x centimeters, the surface area of the cube is capital S, and the volume is capital V. Additionally, we are told that the surface area is increasing at a constant rate of 4 square centimeters per second, and we need to show that dx dt, the rate of change of the edge of the cube, is k over x, where k is a constant to be found. Well, let's start by writing down an expression for the total surface area capital S, which is equal to 6x squared, because we've got 6 identical faces, each with an area of x squared. This means that ds dx is simply going to be 12x. And we also have that ds dt, the rate of change of the area with respect to time, is 4 square centimeters per second. So we're looking for dx dt. I will be applying the chain rule of differentiation here. It's going to be dx ds times ds dt. So the dx ds is simply the reciprocal of ds dx we got here. So that's going to be 1 over 12x times ds dt, which is 4. So we're looking at 4 over 12x, which is of course 1 over 3 over x, and therefore the constant k is 1 over 3. In part B, we need to show that dv dt is v to the power of p for some constant p to be found. So we know that the volume is simply going to be x cubed. So dv dx is equal to 3x squared. So we are looking for dv dt. So once more, I will be applying the chain rule of differentiation. It's going to be dv dx times dx dt. So dv dx, we found this to be 3x squared. Dx dt is a third over x. So this simplifies to simply x. And since we know that v is x cubed, we can easily see that v to the power of 1 over 3 is x. And therefore dv dt is equal to v to the power of a third, which means that the constant p is simply a third. In 3i, we need to use integration by parts to evaluate this integral, giving our answer in its simplest form. So I will start by setting u to be x squared and my v dash to be e to the 2x. Remember, we are always setting u to be that part which will become simpler upon differentiation. So if u is the quadratic x squared, then u dash is going to be 2x, which is simpler. Now v, I will integrate e to the 2x to get 1 over 2 e to the 2x. So the integral from 0 up to 4 of x squared e to the 2x dx, it's going to be uv, so x squared over 2 e to the 2x from 0 up to 4 minus the integral of 2x times a half e to the 2x dx with limits being 0 and 4. I will substitute the upper limit to get 4 squared over 2 times e to the 2 times 4, which is 8. And if we substitute the lower limit of 0, because of the x squared term here, it's going to be 0, so minus 0. And then we've got minus the integral of x e to the 2x dx from 0 up to 4. So obviously, I need to go once more to integration by parts on this integral here. So I will be setting my u to be x and my v dash to be e to the 2x. So u dash is 1 and v is a half e to the 2x. So the integral of x e to the 2x dx from 0 up to 4 is going to be x over 2 times e to the 2x from 0 up to 4 minus the integral of a half times e to the 2x dx, and finally we can see that we've got an integral here which is available analytically. So if I put the upper limit of 4, I get 4 over 2 e to the 8, and the lower limit gives me a 0. And if I integrate the half e to the 2x, I'm getting e to the 2x over 4. So the limits here are 0 and 4. I will proceed in simplifying all of this. So we are looking at 2 e to the power of 8 minus e to the 8 over 4. And if I substitute the lower limit of 0, e to the 0 is 1. So we're looking at minus 1 over 4, which leads to 2e to the power of 8 minus e to the power of 8 over 4 plus a quarter, simplifying to 7 e to the power of 8 over 4 plus 1 over 4. And now it's the time to put everything together. I've got the numerical value of this integral here, and therefore we can say that the integral from 0 up to 4 of x squared e to the 2x dx is equal to 8 e to the power of 8 minus 7 e to the 8 over 4 plus 1 over 4. I will expand this to get 8 e to the 8 minus 7 e to the 8 over 4 minus 1 over 4, which simplifies to 25 e to the power of 8 over 4 minus 1 over 4, which is the final answer for the first part of this question. In II, we need to use integration by substitution to show that the given integral here gives me a plus ln b, where a and b are constants to be found. Well, we know that in integration by substitution, we're trying to re-express the given integral into a simpler integral that can be found analytically. So in this case, we can see that the 2x minus 1 squared is what's making the given integral more complicated. So I'm considering of setting u to be 2x minus 1. So in integration by substitution, we are trying to translate everything from x into u. So this includes the dx, the expression to be integrated, and the limits. So we are looking at du being equal to 2 dx. We can also rearrange here to get u plus 1 is equal to 2x, and I will proceed with the limits. When x is 3, we get that u is 2 times 3 minus 1, which is equal to 5, whereas when x is 21 over 2, we get the u is 2 times 21 over 2 minus 1, which gives an answer of 20. And therefore the integral from 3 up to 21 over 2 of 4x over 2x minus 1 squared dx can be thought as the integral from 3 up to 21 over 2. I will split the 4x as 2x times 2, and we've got the 2x minus 1 squared in the denominator. So the new limits are 5 and 20 respectively. The 2x here will be replaced with u plus 1. So let me write this, it's u plus 1 over 2x minus 1 squared, which is simply u squared, times du, because the 2 dx was simply the du. So I have expressed everything in terms of u, and I see something a lot simpler. This is the integral from 5 up to 20. Well, u over u squared is 1 over u, and 1 over u squared is u to the minus 2 du, leading to ln of the absolute value of u plus u to the minus 1 over minus 1, with the limits being 5 and 20. So we're looking at ln u minus 1 over u between 5 and 20. I will be substituting the upper limit of 20 to get ln of 20 minus 1 over 20, and I will be substituting the lower limit of 5 to get ln 5 minus 1 over 5. Well, ln of 20 minus ln of 5 can be written as ln of 20 over 5, whereas the minus 1 over 20 minus the 1 over 5 will give me plus 1 over 5. So we're looking at ln of 4 plus 3 over 20. In 4a, we need to prove by contradiction that for all positive numbers k, we've got k plus 9 over k being greater than or equal to 6. Well, in proof by contradiction, we always start with the negation of what we are asked to prove, which means the opposite of the statement given here. So we say suppose not, i.e. there exists a positive k such that k plus 9 over k being less than 6. Well, since k is positive, since k is greater than 0, I can multiply throughout by k without having to worry about changing the direction of the inequality, leading to k squared plus 9 being less than 6k. I will be collecting everything on the left hand side to get k squared minus 6k plus 9 being less than 0, which I should recognize as a perfect square. So we're looking at k minus 3 all squared being less than 0, which we know is certainly false, because if we square any number, the result has to be greater than or equal to 0. So we say contradiction, since k minus 3 all squared is greater than or equal to 0 for all real k, and we are missing the conclusion. So we conclude that k plus 9 over k is greater than or equal to 6 for all positive k. We're then asked to show that the result in part A is not true for all real numbers. Well, we have shown that it's certainly true for positive numbers of k. So I will consider a negative value for k. I will consider k is negative 1. Well, if I substitute into the left-hand side of the inequality, the k plus 9 over k becomes minus 1 plus 9 over minus 1. This gives me a result of negative 10, which is less than 6. It's not greater than or equal to 6, and therefore the statement is not true for all real numbers. So what we've been asked to do here is actually provide a counterexample to the given statement, which means a particular numerical value for k that shows that the given statement is not always true. In question 5, we've got a sketch of the curve C with the equation given here. K is a positive constant greater than 1, and we need to find the y dx in terms of x and y. So we're looking at implicit differentiation here. So that means I differentiate from left to right. I apply all rules of differentiation as usual. If I happen to be differentiating a term in y, then I put a dy dx term as well. So here we go, the derivative of y cubed, it's going to be 3y squared dy dx. The derivative of minus x squared is simply minus 2x. And then I need to apply the product rule of differentiation on 4x squared y. If I differentiate 4x squared, I get 8x and I keep the y. If I keep the 4x squared, then I differentiate the y to give me dy dx. And then the derivative of k is 0 as it's a constant. Then I will collect the terms in dy dx on the left hand side to give me 3y squared dy dx plus 4x squared dy dx is equal to 2x minus 8xy. I will factor out the dy dx on the left hand side to get dy dx brackets 3y squared plus 4x squared is equal to 2x minus 8xy, and therefore dy dx is equal to 2x minus 8xy, and all of it divided by 3y squared plus 4x squared. We then have that the point P lies on C. The normal to C at P has equation y is x, and we need to find the value of k. Well, if we start by spotting that the gradient of the normal is 1, we can easily conclude that the gradient of the tangent is -1. And if we recall that the y dx is exactly this as obtained in part A, then we've got essentially that y is equal to x and the y dx is equal to -1. So I can substitute this to get -1 is 2x minus 8x times x. So I'm substituting y with x over 3x squared plus 4x squared, leading to -1 is 2x minus 8x squared over 7x squared. Well, if I cross multiply, I get -7x squared is equal to 2x minus 8x squared. And therefore we're looking at x squared minus 2x is equal to 0, which means that x brackets x minus 2 is 0, which means that x is 0 or x minus 2 is equal to 0, and hence x is equal to 2. Now, if we recall the graph that we were given, we can easily see that the origin, the x is 0, y is 0, is not the point we are after. We're actually after the point at x is 2. And since y is equal to x, we can easily conclude that y is equal to 2. And if we recall that the equation of the curve was y cubed minus x squared plus 4x squared y is equal to k, I will be substituting x is 2 and y is 2 to get 2 cubed minus 2 squared plus 4 times 2 squared times 2 is equal to k, which gives a value of k which is equal to 36. In question 6, we've got the two lines L1 and L2, and we are told that they meet at point P, and we need to state the coordinates of P for a mark. The fact that the prompt is to state, not to find, determine, or calculate, means that it's something obvious, and we can spot that the position vector of both lines is the same, so we can safely conclude that the point P has coordinates 2, 3, -7. We're then told that the angle between the two lines is theta, and we need to find the value of cos theta, giving our answer as a fully simplified fraction. So I will be using the dot product here. I will be dotting the direction vectors of the two lines. So we've got 1, 2, 2, dot the 4, -1, 8 being equal to the magnitude of 1, 2, 2 times the magnitude of the 4, -1, 8 times the cosine of theta, where theta is the angle between the two lines. Well, when I apply the dot product, I do I times I plus j times j plus k times k. So we're looking at 1 times 4 plus 2 times -1 plus 2 times 8 being equal to 1 square plus 2 square plus 2 square. This is the magnitude of the direction vector of the first line, and I take the square root, times 4 squared plus -1 squared plus 8 squared. That's the magnitude of the direction vector of the second line times cos of theta. This leads to 18 being equal to 27 cos theta. And if I divide both sides by 27, we get that cos theta is equal to 2/3. We then have that the point Q lies on L1, where lambda is 6, and we've got another point R lying on L2, such that the triangle QPR is isosceles, with PQ being equal to PR, and we need to determine the exact area of triangle QPR. I will start by substituting lambda is 6 into the equation for the first line to obtain the position vector of point Q. So the vector OQ will simply be 2, 3, -7, plus 6 times the direction vector, which was 1, 2, 2, and this gives an answer of 8, 15, 5. This is the position vector of point Q. So it makes sense to draw a quick sketch to see exactly what's happening. We've got the two lines L1 and L2. We already determined that they meet at the point P with coordinates 2, 3, -7, and Q has coordinates 8, 15, 5. The angle between the two lines is theta. If I join Q and R together, we're trying to determine the area of the shaded triangle shown here. So it makes sense to try and find the size, the length of PQ, because we have been told that PQ and PR are the same, because PQR is isosceles. So PQ is gonna be 8 minus 2 squared plus 15 minus 3 squared plus the 5 minus the negative 7 squared and all square root. This gives an answer of 18. So we know we're looking at an isosceles triangle with PQ and PR having a length of 18. And it therefore makes sense to try to obtain the value of sine theta based on the fact that we know that cos theta from part B is 2/3. So I draw a right angle triangle. Theta is there. The cosine of theta is 2/3. So I can use Pythagoras to get that the opposite here has a length of 3 squared minus 2 squared, which is root 5. And therefore we conclude that sine theta is equal to root 5/3. And I can proceed with the area of the triangle being a half AB sine C. So the area of triangle PQR is a half times the 18 times the 18 times the sine of theta, which is root 5/3, which gives an answer of 54 root 5 units squared. In part D, we need to find the coordinates of the possible positions of point R. Well, we know that point R lies on L2, and therefore we can express its coordinates in terms of the scalar parameter mu. So R has coordinates 2 plus 4 mu, comma 3 minus mu, comma minus 7 plus 8 mu. We also know that the distance between P and R is 18, so I can find an expression for the distance PR, which is gonna be 2 plus 4 mu minus 2 squared plus 3 minus mu minus 3 squared plus negative 7 plus 8 mu minus the negative 7 squared and all square root. This gives an answer of 16 mu squared plus 64 mu squared and all square rooted, and we know that this is equal to 18. So I can remove the square root, I can collect the mu squared, I get 81 mu squared is equal to 18 squared, which is 324. If I divide by 81, I get that mu squared is 4. And so mu is plus minus 2. So two possible values for mu, leading to two possible positions for point R. Well, if mu is equal to 2, then we get that R has coordinates 2 plus 4 times 2, comma 3 minus 2, comma minus 7 plus 8 times 2. And therefore we conclude that the first possible position for R has coordinates 10, 1, 9. Whereas for mu being equal to negative 2, I'll just repeat the process, this time substituting mu is negative 2 to get 2 plus 4 times negative 2, comma 3 minus the negative 2, comma minus 7 plus 8 times the negative 2, and therefore the second possible position for the point R is minus 6, comma 5, comma minus 23. In question 7, we are monitoring the number of goats on an island. Initially, we had 3,000 goats, and we are told that the number of goats x in thousands is modeled through this equation, where k is a constant and t is the number of years after monitoring began. We need to show that k is 1.8, and I will be using the initial condition that when t is 0, we have that the population is 3,000, so x is 3. This means I can substitute to get 3 is equal to k times 9 times 0 plus 5 over 4 times 0 plus 3. This leads to 3 is equal to 5k over 3. If I cross multiply, I get that 9 is equal to 5k. And if I divide both sides by 5, I get 1.8 is equal to k as required. We're then taught to calculate the long-term population of goats predicted by this model. So this is the equation of the model here after we have found k to be 1.8, and what we need to do is consider the value of x as t gets larger and larger. So what I can do is I can go on my calculator, I can put a very big number on my answer key, and then I will simply do 1.8 times 9 ans plus 5 over the 4 ans plus 3. So we are mimicking the behavior of x as t gets infinitely large. I press the equal sign, I get 4.05. So all of this simply means that as t tends to infinity, x tends to 4.05, and since we are talking about 1,000 of goats, the population would be 4,050 goats for the long-term behavior of the model. We're then given a second model where the number of goats x is modeled through this differential equation, and we need to start off by writing this in partial fraction form. So we're looking at 3 over x times 9 minus 2x, which I will decompose as a over x plus b over 9 minus 2x. Obviously, the lowest common multiple is the x times 9 minus 2x, and to get rid of the denominators, I will multiply throughout by the LCM, leading to 3 is equal to a times 9 minus 2x plus b times x. Now I can choose any value of x I want, and this will still be true because we're looking at an identity, and obviously if I set x to be 0, then I'm eliminating this term here. So x is 0 means that 3 is equal to a times 9 minus 2 times 0. We get 3 is equal to 9a, and therefore a is equal to a third. Now another nice value of x will be the value of x that will make this bracket 0, and obviously that will be x is 9 over 2. So setting x to be 9 over 2 leads to 3 is equal to b times 9 over 2. So this means that if I multiply both sides by 2, I get 6 is equal to 9b, and therefore b is equal to 2 over 3. I still need to write down the partial fraction decomposition. So we're looking at 3 over x times 9 minus 2x is equal to 1 over 3 over x plus 2 over 3 over 9 minus 2x. In part D, we need to solve the differential equation with the initial condition to arrive at this equation for x in terms of t. Well, this was the differential equation we were given, and I will start by separating the variables, which means I will be collecting the x with the x on the left hand side and the t's with the t on the right hand side. So this leads to 3 over x times 9 minus 2x dx is equal to dt, and I integrate both sides. Now we can recognize the left hand side here as the expression we have expressed in partial fractions in the previous part of this question. So we're looking at the integral of 1 over 3 over x plus 2 over 3 over 9 minus 2x dx, and obviously I can proceed with integrating the right hand side, which will give me simply t plus c. Now the integral of 1 over 3 over x is simply 1 over 3 ln of modulus of x, whereas the integral of 2 over 3 over 9 minus 2x will give me 2 over 3. I've got the ln of the modulus of 9 minus 2x, but I also need to divide by the derivative of the 9 minus 2x, which is negative 2. So I divide by negative 2, and this is equal to t plus c. So we're looking at a third ln of x minus 1 over 3 ln of 9 minus 2x is equal to t plus c. I will be using the initial condition that when t is 0, x is 3 to determine the value of c. So we're looking at 1 over 3 ln of 3 minus 1 over 3 ln of 9 minus 2 times 3 is equal to 0 plus c. So we're looking at a third ln 3 minus a third ln 3 is equal to 0 plus c. Obviously c is equal to 0. So we've got 1 over 3 ln x minus 1 over 3 ln of 9 minus 2x is equal to t. Remember, we're trying to get this in the form of x is 9 over 2 plus e to the minus 3t. So it makes sense to start by multiplying throughout by negative 3. So this leads to minus ln x plus ln of 9 minus 2x is equal to minus 3t, because I see the e to the minus 3t in the answer I need to arrive at. So I make these adjustments so that I've got more chances of getting to the correct answer quickly. So the left hand side can be combined in a single logarithmic term. It's ln of 9 minus 2x over x, and this is equal to minus 3t. So obviously the next step is to write 9 minus 2x over x is equal to e to the minus 3t. I will cross multiply to get 9 minus 2x is x e to the minus 3t, leading to 9 is equal to 2x plus x e to the minus 3t. I will factor out the x on the right hand side to get 9 is x brackets 2 plus e to the minus 3t, and therefore 9 over 2 plus e to the minus 3t is equal to x as required. And finally, in part E, we need to find the long-term population of goats predicted by this second model. So this is the equation of the model. Once more, I'm going to go on my calculator. I will input a really big value for my t. I store it on my answer key, and I will simply do 9 over the 2 plus e to the minus 3 times my answer key. So this leads to 9 over 2. So we've got that as t tends to infinity. Then we can see that x goes to 9 over 2. What has happened here is that the e to the minus 3t goes to 0 as t goes to infinity. So I'm left with the 9 over 2. And therefore we conclude that we are looking at a population of 4,500 goats as a long-term population. In question 8, we've got a sketch of the curve C described parametrically here. T takes values between 0 and pi over 2. We are told that the curve meets the y-axis at 2 and the x-axis at k, where k is a constant, and we need to state the value of k. Well, we know that we pass through the point k, 0, so we've got that when x is k, y is equal to 0. So using the fact that y is equal to 0, I will say that 0 is equal to 2 cos of t. So we need cos t to be 0, and that's obviously when t is equal to pi over 2. And x, which is k, is 6 pi over 2 minus 3 sine of 2 pi over 2. Well, this simplifies to simply 3 pi, which is the value of k. We then have to use parametric differentiation to show that dy dx is lambda cosec t, where lambda is a constant to be found. So let's recall the equations for x and y in terms of t. I will be finding dx dt and dy dt. So dx dt is simply 6 minus 3 times 2 cos of 2t, whereas dy dt is equal to minus 2 sine t. Looking at the expression we have for dx dt, I could expand this to get 6 minus 6 cos of 2t, and we know that the cosine of 2t is equal to 1 minus 2 sine square t. So I could replace the cosine of 2t with 1 minus 2 sine square t. Obviously the 6 with the negative 6 will cancel out, and I'm left with 12 sine square t for dx dt. So dy dx is simply dy dt divided by dx dt. So I will be substituting dy dt with negative 2 sine t and dx dt with 12 sine square t. Obviously the 2 with the 12 leave me a 6 in the denominator, and I'm left with the sine t in the denominator as well. We know that 1 over sine t is cosec t, so this is simply negative 1 over 6 cosec of t. Now the point P with parameter t is pi over 4 lies on the curve C. We are told that the tangent at the point P cuts the y-axis at the point N, and we need to determine the exact y-coordinate of point N. So let's start with the fact that we've got t is equal to pi over 4, and I can proceed in finding x and y. So x is going to be 6 pi over 4 minus 3 sine of 2 pi over 4. This gives an answer of 3 pi over 2 minus 3. This is the x-coordinate of point P. And for the y-coordinate, we've got y is equal to 2 cos of pi over 4, which is equal to root 2. I will also find the value of dy dx because I want to find the gradient of the tangent when t is pi over 4, which is going to be minus 1 over 6 cosec of pi over 4. This gives an answer of minus root 2 over 6. And using the fact that the equation of a straight line passing through x1, y1 with a gradient of m is given by y minus y1 is mx minus x1, we're looking at y minus root 2 is equal to minus root 2 over 6 times x minus the 3 pi over 2 minus 3. This is the equation of the tangent. And since we've been told that the tangent cuts the y-axis at the point N, we know that if we are cutting the y-axis, this means that x is 0. So I will substitute x is 0 here, leading to y minus root 2 is equal to minus root 2 over 6. And if we put x to be 0, I'm simply left with minus 3 pi over 2 plus 3 within the bracket. So we've got y minus root 2 is equal to root 2 pi over 4 minus root 2 over 2. And if I collect everything on the right hand side, you get that y is root 2 pi over 4 plus root 2 over 2. Now the region bounded by the curve, the x-axis and the y-axis is rotated through a full revolution to give a solid. We need to show that the volume of this solid is given by this integral where alpha and beta are constants to be found, and then proceed with algebraic integration to find the exact volume of this solid. Well, let's recall from the curve given that if we rotate it about the x-axis, this is a kind of solid that is formed. We know that the value of k is 3 pi for x, which corresponds to a value of t for pi over 2. Let's also recall the parametric equations for x and y, as well as the fact that dx dt is 12 sine squared t. Well, we know that the volume of revolution is given by pi, the integral of y squared dx, from x is 0 up to x is 3 pi. But since y is given in terms of t, we've got the parametric equation for y. This becomes pi, the integral of y squared dx dt times dt, and the limits change. The 0 and the 3 pi were x limits. Now when x is 0, t is also 0. So if I put t is 0 here, I get x is 0. So the lower limit is still 0. But the upper limit changes from 3 pi in x into pi over 2 for t. So the new limits are 0 and pi over 2. So we are looking at pi, the integral from 0 up to pi over 2. Y squared is 2 cos t all squared, and dx dt is 12 sine squared t dt. I will take the 12 out, so it's 12 pi, and the integral from 0 up to pi over 2 of 4 sine squared t cos squared t dt. Now the 4 sine squared cos squared should be recognized as 2 sine t cos t and all squared, so it's 12 pi. The integral from 0 up to pi over 2 of 2 sine t cos t and all squared dt, which is of course the double angle for sine. So it's 12 pi, the integral from 0 up to pi over 2 of sine squared 2t dt. Now we know that cos of 2a is equal to 1 minus 2 sine squared a. So 2 sine squared a is 1 minus cos 2a. And if I substitute the a with 2t, we get that 2 sine squared 2t is 1 minus cos of 4t. So it would be great if I was seeing 2 sine squared 2t here. So what I will do, I will write 12 as 6 times 2 and get the 2 within the integral. So it's 6 pi, the integral from 0 up to pi over 2 of 2 sine squared 2t dt. So this is 6 pi, the integral from 0 up to pi over 2 of 1 minus cos of 4t dt. Now to find the volume, I will simply evaluate this integral. So it's the 6 pi there. The integral of 1 is simply t. The integral of cos 4t is 1 over 4 sine of 4t. And we've got limits of 0 and pi over 2. Well, if I substitute the upper limit, I get pi over 2 minus 1 over 4 sine of 4 pi over 2. And if I substitute the lower limit, it's simply 0. So to evaluate all of this, we just need to see that the sine of 4 pi over 2 is 0. So all in all, this gives me 3 pi squared.